Hi, chemistry students. Today we're going to talk about the atom. The first thing that I'd like to discuss is Dalton. Dalton lived in about 1800 AD, so not too terribly long ago, but still quite a ways. His atomic theory stated a few different things. He stated that matter is composed of atoms, which are indivisible and indestructible. So we do know that matter is composed of atoms. We can all agree on that. However, the theory that states that they're indivisible and indestructible, I wouldn't go so far as to say that. So remember, he was theorizing all these things hundreds of years ago before we had discovered ways to split the atom, before atomic bombs were a thing, before all of those things existed. So on the whole, he's correct. It's very, very difficult to split an atom, but it is not actually impossible. Atoms of an element have the same size, mass, and chemical properties. So again, he theorized that pretty much if you have one atom of gold and another atom of gold, they are the same. Which again, on the whole, correct. There are things called isotopes where atoms of the same element can have slightly different masses and slightly different chemical properties depending on how many neutrons they have. But again, this was hundreds of years ago. He theorized that each element's atoms are different. So if you have an atom of gold, it's going to be different than an atom of uranium. True, accurate. He theorized that different atoms combine in whole number ratios to form compounds. So if you wanted to form salt, a sodium atom, a chlorine atom can come together and bond with one another. Accurate. And he theorized that chemical reactions separate, combine, or rearrange atoms, which is, again, perfectly accurate. It's a beautiful description of how chemical reactions work. Okay, so if we're going to talk about atoms, we have to talk about atomic particles, otherwise known as subatomic particles. You may have heard that term before. Protons are one of them, and they are a particle with a positive charge, and they are located in the nucleus of atoms, or the center of atoms. Their symbol is P+. So if you ever see me write P+ on the board or anything like that, you'll know I'm talking about a proton. They have a mass. They weigh 1.007276 AMU. AMU stands for atomic mass units, which is the unit of measure for measuring the mass of subatomic particles. We have neutrons, which are particles that carry no electric charge, and they are also contained in the nucleus. Their symbol is N. Sometimes I'll abbreviate it as an N with a slash through it. It just kind of depends, but that also is going to indicate neutron. They are slightly heavier than protons with a mass of 1.008665 atomic mass units. And last but not least, our third subatomic particle is the electron, which is negatively charged and found in all forms of matter outside of the nucleus. You don't find electrons within the nucleus of an atom. They orbit the nucleus instead. Their symbol is E-, and their mass is what we like to call negligible. They do have a mass, it's just very, 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 very small. So more or less, when we're factoring weights into atoms, we just say that their mass is approximately 0 AMUs. Like I said, they do have a mass, it's just tiny. So here is a generic drawing of an atom. You see the electron with that minus in it in blue orbiting the atom. You see the proton in red with the plus in it, and the neutron in green with no symbol in it, because neutrons do not have a charge. If we're getting technical, this is actually a hydrogen atom, one of its isotopes, but a little bit later in the presentation, I'll talk more about isotopes. Important numbers to be aware of. Atomic number is the number of protons and the number of electrons. But one thing that I want to say about this is atomic number is always the number of protons that an atom has. However, the number of electrons in an atom can differ. And when atoms attain a charge, either positive or negative, suddenly they're going to have different amounts of electrons. So when I say that atomic number equals the number of protons and electrons, I'm saying that in neutral state, when that atom is neutral, protons and electrons will equal one another. And that will become important later when we talk about atoms with charges. Another number to be aware of and understand the term for is atomic mass, which is you take the protons and the neutrons and you add them together to get the atomic mass. Okay? So when I see you back in class eventually, I'm going to hand you a periodic table that you'll use for the year. But you'll use the electronic form for me several times before that. And what I want you to be aware of are a few things. In each square, you're going to find the name of your element, either at the top of the square or the bottom. It kind of depends on which version of the periodic table you have, but it'll be there. The top number here, this number 1, is going to be your atomic number or your number of protons. You're going to see the atomic symbol, which is the letter H in the case of hydrogen. Helium is He, so on and so forth. And then below that, you're going to have the atomic mass, which, remember, is the number of protons and neutrons in an atom. Hydrogen usually, 99% of the time, is going to look like this, and I'm going to draw it out for you. It's going to have a proton, and it's going to have an electron kind of orbiting, and this dotted line is representative of the electron's path around the nucleus. So this is most hydrogen atoms. So you would think that hydrogen's mass would just be 1, because I told you that electrons basically weigh nothing. But there is a discrepancy here that has to do with the different isotopes. So understand that these 0.008 in the case of hydrogen or other decimal values have to do with the isotopes, okay? So isotopes are, to define them for you, atoms with the same number of protons, but different numbers of neutrons. So to draw that out and just kind of explain a little bit more, I'm going to use hydrogen again. So I told you that most of the hydrogen on planet Earth, we have the 1 proton with 1 electron kind of orbiting around like that. Really, it doesn't orbit in a concentric circle like that, but for our purposes, we're going to use that diagram. So that's one form of hydrogen, okay? However, there's another form that looks like this. We have a proton and a neutron with that 1 electron kind of orbiting around. And there's a third form that exists as well, which is 1 proton and 2 neutrons with that electron orbiting around. Now, these are all hydrogen, and we know that they're all hydrogen because they all have 1 proton, and your proton is what gives your atom its identity. So we know that since, hey, 1 proton, 1 proton, 1 proton, it's all hydrogen. But the neutron amounts gives us these 3 isotopes. So if you look at their atomic masses, this one is going to have an atomic mass of 1, this one's going to have an atomic mass of 2, and this one's going to have an atomic mass of 3. So when we calculate something called average atomic mass, we have to factor in these other 2 isotopes, okay? So average atomic mass is the mass on the periodic table. So under every element, that atomic mass that you see is an average, and it is factored in with each of the known isotopes for that element. And you calculate it with using this formula right here, and I'm sorry, my drawing's a little bit in the way, but the mass of your first isotope times its percent abundance, plus the mass of your second isotope times its percent abundance, plus the mass of your third isotope times its percent abundance, so on and so forth. So to explain what I mean by that, if we just flat took the average of these 3 isotopes and had done with it, we would end up going 3 plus 2 plus 1, which equals 6, and you divide that by 3. Now, if we took the raw average and we did 3 plus 2 plus 1, over 3, that's going to give us 2. But that's not the mass that we see on the periodic table. We see 1.008 on the periodic table, and that's because these two isotopes are very rare. They represent not a lot of the total hydrogen on planet Earth. Like I said, about 99% of Earth's total hydrogen, a little bit more probably, is represented by this isotope right here. So that's why the average atomic mass of hydrogen is so close to 1. It's because this is most of the hydrogen on planet Earth. But you have these two isotopes over here, which this one is called deuterium and this one is actually called tritium. So for anybody who has seen the second Spider-Man that had Tobey Maguire in it, Doc Ock was using tritium. This is what they were talking about. Tritium is not solid, so you can't just pull it out of a safe and do things with it, but that's what tritium is, if you were curious. Like I was saying though, these isotopes represent a small fraction of the total hydrogen on Earth, so, or in any given sample even. So that's why our average atomic mass on the periodic table is slightly above 1. And we will be doing some calculations for average atomic mass in the coming weeks. So that's all that I have to say about atoms currently at the moment. We will be learning much, much, much more about electrons and how they move and how they act in the coming weeks. But for now, just make sure you fill out those notes sheets that I gave you, and have a good day.